Okay, geometry class, here we go. This is a little review of algebra. What we're doing is we're jumping ahead to chapter 9. Chapter 9 deals with right triangles, and actually it is extremely important to know and understand how to work this stuff that we learned in chapter 9 in order to move on to pre-calculus, and then if you do any calculus after that, a lot of the right triangle stuff that we learned in chapter 9. So chapter 9, they call it the Pythagorean theorem chapter. But it's really about right triangles and how to use different, there's a lot of rules. You can do a whole class on just right triangle stuff. A lot of trigonometry is based on right triangle trig. And we'll do a little trig at the end of chapter 9. So review of radicals and quadratic equations. This work involves a lot of square root stuff. That's what they call the radicals. And a lot of stuff dealing with x squared. And that's the quadratic. Everybody this year has already taken Algebra 2 last year, so a lot of this is going to be review. This is actually material you should have learned in an Algebra 1 class. So this is stuff that should be a review for everybody in this class right now. All right, let's get into it. So 9-1 is a section. We got to know your what they call perfect squares. So you need to know, like have it memorized, the early perfect squares. These are numbers that you know have even square roots. They square root and they come out evenly. So like 1 is the lowest one, then 4, and then 9, and then 16, and then 25, and then 36, and keep going and going and going. Probably the biggest number you probably should have memorized. Let's see. I think most of you know like 12 squared, 144. You guys know is a perfect square. 169 is 13 squared. And, after that, then they're not really all that common. You might get some bigger square roots after that, and we'll learn how to break those down. So this is going to be just a lot of examples and examples and examples today rather than just note-taking. So lots of examples today. Example A. So it's going to say simplify. Simplify the square root of 48. If you use a calculator, it's probably going to spit out some sort of a decimal. What you have to do is think of what is the biggest perfect square that goes into 48. The biggest perfect square that goes into 48. So the biggest perfect square that goes into 48 is 16 times 3. Whichever one's the bigger perfect square number, put that first because that becomes a regular number 4. And then you have square root of 3. All right, 4 square root of 3. 4 square root of 3. You don't need a plus minus in front of this. That's only if it was like x squared and then your square root both sides. That's when you need a plus minus. Let's say you didn't think of 16 goes into 48 right away. Let's say you thought, well, 48, I can break that down into square root of 4 times square root of 12. And I'm sure there's a couple kids watching the video that said that one first. That's the first one that came to mind. It's fine. You can do that. But then you get 2 and root 12, and you're not done here or here. You're not done if there's another perfect square number that divides into what's under the square root. And in this case, you can break 12 into 4 times 3. And the square root of 4 is a 2. And so it's 2 times root 3. And we get 4 square root of 3. So 4 square root of 3 is the right answer, whether you do it the quick way by finding the biggest perfect square, or you do it where it takes a few steps because you didn't start with the biggest perfect square. Example B. You know what I'll do is I'll use different colors so it pops a little more on the note taken. All right, simplify. Simplify the square root of 128. Square root 128. So this would be one where it wouldn't surprise me if you didn't find the biggest perfect square. Heck, I'm not even sure what the biggest perfect square. There's a lot of perfect squares that goes into this one. 4 goes into that. I think 16 goes into that. But sometimes it helps to just say, well, what happens if you divide the number in half or divide it by 3? Right away, if you divide that number in half of 128 is 64, and that happens to be a perfect square number. Square root of 64 is 8. Square root of 2 is an even number, but it doesn't have any sort of square roots. 8 root 2 is the final answer here. 8 square root of 2. If you started with like a 16, I know 16 goes into it. I actually don't know how many times though. 128 divided by 16. So with a calculator, I just did, hey, 128 divided by 16. Just see what I get. 128 divided by 16. I get 8. So let's say that's what I thought of first was 16 times 8. That would give me 4 and then root 8. But I'm not done because, oh, I'm sorry, it's not on screen. Let's say I said 16 times 8. And then I get square root of 16 is a 4, square root of 8, bring it down. But 8 can't be left. That's because there's a perfect square that goes into 8. 4 times 2 is 8, so that becomes a 2, and 4 times 2 is 8, and you get 8 root 2, same answer. Just took you 2 steps instead of doing it in 1 step. That's all. That's the only difference there. Let's try another one. Give it a little bit of a different look. Example C, I want you to simplify. Let's put a number in front. 3 square root of 32. Do you know how to simplify 3 root 32? 3 square root of 32. So same thing. This 3 in front means like 3 times. So any numbers that we bring out in front just gets multiplied with that 3. So right away, we're going to break this into 16 times 2. Root 16 times root 2. Root 16 is a 4. Root 2 is going to stay square root of 2. 3 times 4, not plus, times. I get 12 square root of 2 when it's all said and done. How about a little adding and subtracting in between? Example D. Example D, I got square root. Now I would say simplify again. Simplify. I got the square root of 18 plus the square root of 32, the square root of 75. It would be like a multiple choice test, like an SAT. They're going to ask, they're going to put the answer down, and they're going to say like, oh, if you just add the numbers together, 18 and 32 together, that equals 50, and then 50 plus 7. So it's square root of 125. Wrong. Dead wrong. We can't add or subtract radicals unless they're the same radicals. I can only add a square root of 2 with another square root of 2. I can only add a square root of 3 with another square root of 3. What you're going to do is simplify each one. They're going to be like their own individual problems. Square root of 18, break it down into 9 times 2. And so you get 3 root 2 when that's simplified. Square root of 32, we just did that one over here. We're going to simplify that into 16 times 2. And that becomes 4 square root of 2. 75, 25 is a perfect square that goes into it, times 3. And so we get 5 root 3. Just like it's almost the same idea that as if I gave you, hey, if I said 3x plus 4x plus 5y, and I said combine like terms, your answer would be 7x plus 5y. It's the same logic here. I can only add or subtract like radicals. So 3 root 2 plus 4 root 2 is equal to 7 root 2. It's 7 square roots of 2 plus 5 square root of 3. That doesn't simplify any further. This does not simplify any further. And that is your exact answer. You don't want any decimal answers here. That's an exact answer. Decimal answers has it rounded off at some point. All right, so let's make a little math note here. I have math note written on my old notes. Math note. We can multiply radicals when they're not alike. That should be one word. When they're not alike. But we cannot add or subtract. But we cannot add or subtract when they're not alike. For that, you need what's known as like radicals. So you might hear the term like, you might hear me say, hey, they got to be like radicals. They got to be the same type of thing. All right, so I can take I can do a square root of 2 times the square root of 3. That equals square root of 6. And then square root of 6 doesn't break down. Okay? But I can't add square root of 2 and square root of 3. Also, all right, also in math, we were not allowed to leave a square root in a denominator. We must what they call rationalize. Actually, the whole thing, rationalize the denominator. So it's just a little extra step. The decimal version of it would be the same. So for example, if, what am I on? Example A, B, C, D, example E, sorry. Simplify square root of 5/3. Not allowed to leave a fraction in a denominator either, okay? But I can't leave a square root over the denominator. And this one technically has a square root over the denominator when you think of it as square root of 5 over square root of 3. Now, neither one simplifies. And I'm going to show you something. I don't even know what it is, but the decimal, let's get the glare out of the way. The decimal version of this, if I go square root of 5, get an answer, divided by second square root of 3, get an answer. I get 1.2909944. We're going to change the look of this, but not change what the decimal version of it is. All right, so I'm not changing the value. We're only changing the look of it. And the way to do that is by rationalizing the denominator. You're going to multiply by a fraction that equals 1. And fractions that equal 1 have the same top and the same bottom. And so we're going to multiply by root 3 over root 3. Now remember, you can multiply radicals that aren't alike. So the top is going to be the square root of 15. The bottom, what it's going to happen is you get the square root of 9. We just made it a perfect square on the bottom. And that's going to equal 3. Square root of 15 divided by 3. And please don't think 15 and 3 reduce. That's not a normal 15. That's a radical 15. All right, and a 3 on the bottom. A radical 15 and a 3 on the bottom. So please don't think that those two will reduce. That decimal here is the same decimal as over here. If I go second square root 15, get an answer, and then divide that by 3, I get the same decimal as up above. They're the same value. They're the exact same value. Okay, just a different look. This is a rationalized denominator. Anytime we put answers down, we can't leave a fraction inside, or we can't leave a square root on the denominator. Then you have to rationalize it. If you have this or if you have this, must rationalize the denominator. All right, next part. I think I got to pause pretty soon. Yeah, I need to pause right. I think I need to pause it right about now. I'm going to pause it right here, jump over to video number 2 for the rest of the lesson and more examples.